and also sometimes KNN, but really it depends on the
Reminder, we posted on Piazza, but we will not be having class next time on Wednesday. So the next class will actually be next Monday.
Cool. Yeah, so it just so happens that the likelihood of all instructors being hit by midterms and examinations on Wednesday at precisely this time actually did happen. So so we're going to be having our next class next Monday, in which we'll talk about random forest and then AWS, where you get to see how you can rent out computers from Amazon. Cool. All right. Before I get started, though, how did everyone feel about Project 2 in terms of? Okay, I see a lot of smiling faces, which is either a good sign or a very bad sign. Yeah.
If our code took a long time to run, we spent a lot more time on this project than.
Okay. So advice I was giving to people who asked me, specifically Kevin, maybe he's not here today, but he asked me how you could speed it up. You could just do it on a subset. So if you ever encounter like a huge data set like that, just do it on a subset to test your hyperparameters, and then try it on the entire set to see how well you perform, I guess.
Yeah, and that won't give you the most accurate model, but it will speed things up tremendously for training. So generally, like if you are validating whatever algorithm or technique you're doing, it is okay if you just do it on a subset. What happens later is that people rent out computers from AWS that can fit everything in the memory, and then once they validate that their method works really well on their local machine using a subset of data, then they rent out a computer AWS to do it for them instead.
And that's something we'll talk about on Monday.
Yeah,
so.
yeah.
It seems like a lot of the other solutions, I think yours also have 800 grids, or 20 by 40, right?
Yeah.
So is there any reason why that was like maybe the most optimal?
So that is not the most optimal, but it was close. It's basically tested. So when I first started writing this script, I also had thought, well, 800 grids, that's very arbitrary. I'm gonna change it up to maybe 1,000. It turns out that if you change it up to more grids, like 1,200, 1,500, your local validation score becomes either widely off or it becomes lower. In terms of how accurate your model can run on these smaller grids. This is generally because intuitively, if you think about it, since each business has some kind of cloud of check-ins around them, you don't want a very small grid size. Otherwise, one business who has like a cloud of check-ins a mile away won't be part of your model. It will actually not see that business at all. Because the grid is too small. Whereas if you have a too big grid, then you have too many businesses offering noise inside your data set, so the model won't be able to distinguish one business from the other that well. So having some kind of playing around with the grid sizes was like in essence its own hyperparameter where we just tune it to see like what was producing the best accuracy. It is not something that we can mathematically like prove, oh, this is the correct number of grids. It was something that people generated from trial and error. Yeah, but also if you went into depth and look at the like other types of scripts out there on Kaggle, there were actually quite a few who didn't just do the grid system, but did the grid system plus like a quarter mile shift to the right, plus another quarter mile shift to the right again. And that was able to capture some of the problems with the borderline like data points, where what if a business check-in just so happened to land on the border? And that problem could be addressed by creating multiple models. Well, in this case, just 4 models where you're just shifting it by a quarter, another quarter, and a quarter. And then ensembling the predictions together. We'll get to talk about ensembling actually when we talk about random forest, but there's a more general idea of ensembling we'll talk about later. Yeah, so back to the question of the grid size, that's completely by trial and error. So, yeah.
Instead of doing it this way, I think that like since it was kind of slow on our computers, could you potentially like find like maybe the number of rows and columns you should have used so that each
Are you talking about the something similar to the benchmark script, or the ZF Turbo script that I showed you guys on
So you're saying
Wednesday?
basically like abandoned data science methods and just like say like, if I can just throw it into this certain grid, if I can analyze that it probably is within this grid, I can actually just assign an accuracy score from that, right?
Yeah.
I mean that's definitely a way to do it, but it still would probably not have the high accuracy that you would expect from maybe an algorithm actually doing that as well. So that is the point of the grid system. It's just to give like that kind of fine resolution, and then additionally apply like the data science technique onto it.
All right, cool. Did I answer your question? Awesome. Anything else? Cool. All right, so guess we'll get started. So outline for today, majority is going to be about decision trees, and then I'll introduce random forest a little bit at the very end. So just to begin, some motivation of why we have this model in the first place. Imagine that we have a data set of a very simple data set with 3 columns: age, a question called has job, whether this person is employed or not, and finally owns car. So owns car is going to be our response variable. We want to see, based off of someone's age and whether this person is employed, how likely is this person to have had a car or own a car currently. So questions about just literally just staring at this data set. How would you split each column to make a particular decision? So you can split based off age values, or you can split by the has job column. How would you yourself, when you're looking at this data, parse the rows to form your predictions? Any guesses? Again, this is not supposed to be something very complicated. I'm just trying to drive what us humans would try to do in order to divide this data set up. So how would I divide these columns such that I can predict whether someone owns a car or not? Anyone? No one? Okay, yeah.
If the age is less than 17, they're probably not going to have a car.
Yeah, so first thing you can split here, if it's less than 17, probably not have won't own a car. But what about if a person is is over the age of 17? Can we split this up even further? Yeah.
The age is over 17, or if they have a job that's over 18, they won't have a car.
Yeah, so we're now combining 2 columns. So first is the age is, did you say over 18? Okay, yeah, so over 18, that's one way. And then we look at the second column. Does this person have a job? If yes, we'll predict a 1. Otherwise, we'll predict a 0. So the next slide here shows. I didn't really know what was the best color scheme for this, but I'll try to explain as best as possible. Basically, we are splitting first by the age column. Anyone who's greater than 18 years old will be reflected as brown, and then anyone who's less than or equal to 18 years old will be reflected as dark green. And then basically, we can basically say that anyone who's less than or equal to 18 years old will not own a car, according to this data set. And we don't even need to look at the has job column at all. Whereas for people who are over the age of 18, we need to split further because we're not still guaranteed between like a definite 0 or definite 1. So that's when the second column comes into play, where we split again by whether this person has a job or not. And if this person has a job, then out of the people who are over age 18, we're going to predict that this person owns a car. And if the person does not own a job, then or have a job, then this person does not own a car. So does that make sense for people? We're literally just splitting the data set visually in this case to make our decision. And so this lends itself to really a series of decisions where we naturally look at each column, try to make splits, and look at another column, try to make more splits in order to get to the final response variable target to be either 0, 0, or 1. So this is another representation of the slide before, except this is probably the more common representation of what we call decision trees. So we start with the first variable that we're going to split by at the very top here, called age. And then you notice that there's like a less than or equal to 18 title over here. Basically, if we feed in a particular row, like say this row, inside this decision tree. We're going to look at the age column. We're going to see if the age column's value, in this case 12, is less than or equal to 18. If that is true, then we go to the right. We don't, technically, this is wrong. We don't even need to look at the hash job column, but it goes straight down to 0. So if we fed in like each data point, each data row, we're going to like traverse this tree into the individual buckets. So if we have this column instead, like this person age 45 does not have a job, into our decision tree, then we meet less than or equal to 18. That is false. This person's age 45, so we'll go to the left. Then we looked at the second column, has job column. We want to see if there's a 1 in that column or 0. In this case, this row has a 0. So that means this is not true. This is not 1. So we go to the left, and we predict that this person does not own a car. And then if you add more data, then you can feed in more of the rows, and then eventually be able to traverse this tree to whichever value at the very end. So that is the what I think the bears of what decision trees are. It's really just trying to split the data set into very simple decisions that we naturally would do if we were trying to stare at this and do it ourselves. So this is a more expanded example taken straight from Python's sklearn's documentation about decision trees. You will get to learn about what all of these numbers mean by the end of this class. But basically, just overall, we can see that. Actually, can you even see that? Can I even zoom here? Well, if you squint very hard, then you see that the top line will indicate some kind of variable. Okay, so yeah, in this data set, we are trying to predict, I think, 3 different types of flower. I forget, like plants of some sort, called the iris data set. And we have different attributes like petal length, sepal length, petal width, etc. And then the first line of these boxes represent which column we're looking at, and also which value that we're splitting at inside that column. And if it's true, then in this case, we're going to the left. If false, we go to the right. So, and notice that these decisions are always binary. It's either a yes or a no. We're splitting literally everything by cutting the column in some place. So we do that a bunch of times, and then these decision trees just branch out and become much longer and more complicated depending on how large your data set is and how complicated it is to make a decision. So any questions so far? Cool. All right, so I'm going to teach you how to generally how these decision trees are made. And like before in linear regression, logistic regression, we want to minimize the error that we have in the very end. So for regression type problems, which are predicting values between continuous values like your GPA, for example, house prices, for example, these kinds of things, we want to minimize the error of the SSE, which you guys were introduced to way back when we talked about when we were talking about how to minimize the objective function of a linear regression equation. So that should be already familiar, which is basically trying to calculate the error within these residuals over here. The true value minus the predicted value, square it, then you sum all of these values up together to get your SSE. And that value is the final value that we're trying to minimize. All right, so what about classification problems, where we have, instead of a continuous set of values, we have discrete values, and these discrete values correspond to different classes. So in the Facebook project, you guys had to predict multiple businesses, more specifically their IDs, and that's a very concrete example of what I mean about classification. So sorry, I'm a little bit sick, so I'm going to be coughing a little bit. So a little bit about how to measure the error of our classification. So we're going to be using something called the Genie index, which is very popular out in the real world when you're running these random forests, and then you're measuring how important variables are. This is one of the more common measures of how to evaluate whether a variable was important in your model when when the model is already finished. So the Genie equation is basically this equation right over here, which is the probability of a certain class in a region M, and I'll get to regions in a little bit, a region a little bit later. That probability times 1 minus that probability. And then you sum it up for all your classes. So that will equate to your Genie index. So I'll give you like a very detailed explanation very soon. So, but first, I want to talk about how to do it for a regression first. So imagine that we have our response values over here. These could be, like I just put these numbers in randomly. This line represents a decision split. So in our tree diagram, we flipped it to the side, we traverse the tree, and then we create a split over here. We basically split the response variables such that we have this half over here and then this half over here. And this is what I mean refer to as regions. So within each region, we want to calculate the SSE of our prediction. So in this case, we're going to always use the average of the values over here as our predicted response. So in this case, we're going to simply subtract 0.1 minus the average of all the top values over here, which happen to be 0.44. You square that, then you do the same operation for 0.5 minus 0.44, square that again, you sum everything up to get final SSE for m equals 0, or the 0th region over here. And then we get 0.352. We do this again for the bottom region. Exact same operation, and then we get a SSE of 0.033. So does that make sense for people? Well, I tried to make this as simple as possible. So so then what do we do after that? Well, we want to combine the two SSEs together, just take the sum, 0.385, and then compare that to what if we hadn't made the decision in the first place? What if we just predicted this and predicted everything to be the average of both regions, and then compute the SSE again? Well, if we did that, we will see that SSE all is actually 0.589. And if we compare that to the combined SSEs of our splits before, we'll see that that SSE was much greater. And that means that when we're making the split, we're trying to get a lower SSE, which if you visualize everything, which is exactly what we want. The closer that the response values are to each other after our decision sets, generally the better our prediction is going to be. So this again is what we mean about minimizing the SSE or minimizing the error. So based off this, we can see that we can see that the split helped. And if this was the only split that we're considering, then we just pick the split and then move on with the rest of the decision tree. In reality, we'll test out all combinations of splits of each variable to see which one of these numbers over here produces the lowest SSE. And then that's how the tree is formed in the regression case. Any questions about that? Cool. All right, so now to talk about how classification works. Same landscape. Imagine that instead of response values, continuous values in the response column, we have classes. In this case, we have two classes, blue and red. And again, we still have the same regions as before. Now, in order to use this equation, we need to plug in the parameters that we want. So again, M is equal to the region. K is the kth class. So first, this is just a very simple exercise. What is our probability of a class, the 0th class, belonging into the 0th region? Just looking at this over here. If you were trying to guess what the probability was, what would it be? can you speak louder?
2/5.
2, yeah, 2/5. Great. How about the first class in the 0th region? 1 minus I, right? 3/5. Cool. And then the 0th class in the first region, so it would be this one over here. What would that probability be? 1/6. Great. And then the reverse will be 5/6. So yay, we got our numbers. Technically, this is literally all we need in order to calculate the Genie index now. So if we use these values, we can now compute the Genie index within each region. So can anyone with quick mental math calculate what the Genie index of the 0th region be? So we're not going to be using any of these values. We're only going to be using the probabilities from the 0th region over here. No? No? Any guesses? Okay, I'll just give you the answer, yeah. So yeah, it's 0.48. And for the first region, we have this fraction over here. So basically, the Gini index is calculated in a very simple manner, and we can do so for every region that we split on. And once we get, before I move on of what to do next, just quick questions, I guess food for thought questions. How do we get a Gini index of 0? Again, this is not supposed to be a terribly difficult exercise. Yeah?
If the entire region is the same.
Exactly. If we had a probability of something that is equal to 1, then the Gini index will equate to 0. And if you think about it, that's exactly what we want. So again, just like in a regression case where we want all the values to be as close to each other as well, together, the Gini index, for the Gini index, we want to have all the classes to be the exact same, so that when we split everything using our decision tree set in our minds, we want to have basically all of the same classes together. And that's generally like what we try to do naturally. So Gini index of 0 is what we're trying to achieve generally. How about what's the highest index we can get for, in this case, a 2-class problem? How do we get the highest index? Yeah.
When it's half and half.
Yep. So if it's 0.5 times 0.5, we get a Gini index of 0.25, and that's the same thing for the second region. So if you sum those two up, we have a total Gini index of 0.5. What about an n-class problem? A little bit harder. 1 over, or some 1 over. So there's something in the numerator, but I think you have the general idea. I think it's n minus 1 over n squared. If you just multiply the two, and then you have to sum up for the other region as well. But generally, in order to get the highest value for an n-class problem, the probability or the ideal probability is 1 over n. And then for a 3-class problem, it would be 1/3 times 1 minus 1/3. That would be 2/9, and then you sum it up for all the classes to get 2/3. So and then I kind of already answered this, but in general, we want to have a lower Gini index when we're trying to split the trees. A high Gini index will basically mean that every single class is, after we split into our regions, every single class is evenly distributed, which is not what we want. So when we're trying to split, again, we want to try to be uniform in the final classes that we get. Cool. So as in before, what do we do after we get the error metrics for each region? We combine them together. We add them all together. We get 0.379. If we did this without splitting and compute the Gini index for this entire region over here, we get a Gini index of 0.397. And again, our split kind of helped, even though the difference is a little bit smaller now. In general, we will want to find the split that will make the lowest Gini index possible. And then going forward through the decision tree, we'll use that split. And then again, recompute all the splits in each column afterwards. Does that make sense for people? Yeah.
So for each step, you can only do one split.
Yeah, for each step, you only do one split. Correct. Any other questions? Cool. And that was a 2-class problem, and I just want to reiterate visually again that this can generalize to any number of classes, and then you just compute the Genie index for each region for all of these classes instead. Cool. So there's that. So that was let's see. Oh yeah. So these steps are just reiterate the stuff that I talked about before. Step 1, you choose your error metric depending on which problem you are in, and then for number 2, you split the column that minimizes the SSE or the Genie index. And then you perform the split that minimizes everything, and then you repeat number 2 until you get to some threshold, until you get to the point where you have, say, only three rows of data inside that particular region. After that, then you just call it quits. You're done. You don't need to move go further anymore. Now, in reality, when I mentioned that we take the sum of these values, in reality, we need to do a bit more to this value. Basically, the implementation of random forest or decision trees in Python or any other language does this logic differently. Instead of taking the average, we take a weighted average corresponding to the number of nodes within within that region. And if you want to know more about why, then I encourage you to go onto YouTube. Just search up how decision trees are made, and then they talk about why exactly that we do the weighted sum instead of the weighted average instead of the simple average. But I just want to let you guys know that this is a very, very simplified method of how we build a decision tree in the first place. The actual implementation is a little bit different, and it addresses some issues that is common when we are trying to split the data in such a manner. Cool. Any questions so far? Awesome. So this is a close-up view of the decision tree that I had earlier. Now you probably, hopefully, can recognize what all of these lines mean. So the first one is, again, which column we're splitting on, and then the value that, which column we're picking, and then which value inside the column we're splitting on. And the second one is the Genie value. Before the splits are even made, we get a Genie value of 2/3, which corresponds to a data set with only 3 classes. If we split based off the first line, we go to the left if a petal length of something was less than 2.45, and then we get to this point where we have 50 rows. That's what samples means. The value basically the value will give you how many of those rows will correspond to, in this case, the 0th class or the first class or the second class, and so all 50 of them belong into the 0th class or the setosis class, and naturally, when all of the rows are of one class and we made a decision split, then the Genie index will naturally correspond to 0. So this is exactly what we have over here. If we go to the right side, again, we have the same format. We have 100 samples, 100 rows now, and they have to be evenly split between 2 classes, Versicolor and Virginica. So 50 over here and 50 over here. And then we get a Genie index of 0.5. And then we split again with going to this criteria, then we get to here and here. And basically now we have a couple, we now have a case where we're very, very close to a Genie index of 0. Basically we have 54 samples over here. 49 of them correspond to one class, only 5 of them correspond to the other. And we have the same case over here. And then again, we can also split this further down more and more until we get Genie indices of 0 at the very end. Or in some cases, stop before we have 0 samples to work with. Okay, does that make sense for people? Yeah?
Wait, how do you choose the number in the first line?
This thing right here.
Yes.
So that is based off like testing different splits in the column. There's a like fast way of figuring what that number is, but you do that for every single column, and then whichever split produces the least SSE or the least Genie index is the split that is chosen at the very top over here. If I can find that, yeah, over here.
It's like the one that creates the splits that are most.
Yeah, so as you can see, we have this split creates 50 of the same class over here, which is great. And then the second region has 50 and 50 of the second and third classes.
Are those values and values supposed to be like the label data points that are in there?
So this is how many are inside our data set.
And
So we have.
We know that because they're labeled, right? They have like the associated labels.
Yeah. Well, I mean, we only have 3 classes, so we don't need to know the labels in particular. This table doesn't show everything. I'll later show you in code like how we can see what those labels are from our model. But I don't think we need to know anything more. Is that something? Okay. Yeah. Cool. All right, so now to introduce random forest. So it actually turns out that if we build a single decision tree, it's actually terrible. Because as you can imagine, if you have a very simple data set and we build a decision tree on just that data set, it will probably overfit that data set pretty well. Just as us humans, if we look at one homework assignment and try to train our minds on just a single homework assignment, we're probably not going to do well on, say, a final or a midterm. So we need to have more of these. And that motivates us trying to build more decision trees of the original data set. So this is what we call a forest. And to go back to what I said about trying to build multiple decision trees, we're not building the same decision tree using the same data. We're actually subsetting the data to have only a fraction of the rows of our original data and feed that data inside our tree. And then we produce another subset to feed into our tree, and then another subset, and another subset, and another subset, so that what we try to get is different decision trees. So each decision tree will look differently because the data that it was trying to be built upon are in every single time different each time. So it's just like multiple homework assignments. You might have some duplicates inside your homework assignments where the problems might be similar, correspond to your previous homework assignment. But in general, there will be some questions that are going to be different. And if you do this a bunch of times, if you go back through past midterm exams or final exams too, you eventually build your multiple models that your mind can work with. So that's the motivation for random forest. The random part of random forest comes from the fact that we are randomly choosing the rows that we're trying to feed our decision tree on, and also importantly the columns too, because the motivation behind that is that sometimes there's one particular column that just always stands out, that always tries to beat every other column in terms of where the best split is made, and that is okay, but again, it's just like feeding in the entire data set into a model. There's always danger of overfitting because that column mathematically will always make the best split. So sometimes, and this has been tested quite extensively, it is best to always have a subset of not just the rows, but also the columns, so that we are not giving all of the data both height-wise and also width-wise. Does that make sense for people? And so again, once we do this randomly every single time, we will get different trees every single time. And so in the end, once we have multiple trees, then we can have multiple, I guess, predictions or outputs. So actually, I forgot to mention previously what we do once we actually once we have built a tree. Again, if we want to predict using some kind of test set, then you just you give it the row, then that then this tree would just would tell you just grab like the appropriate columns, column values from that row, and then you go down this tree and then go to the response value that that it lands in, or whichever bucket it goes to at the very end. And so you do that for every single tree now, and then you get different prediction responses afterwards. So tree 1 will have, say, it predicts a value of 12.06, tree 2, 14, tree 3, 11.59, and then you just take the sum of everything and divide it by the number of trees to get your final prediction of 11.93. For classification, we do the same thing, except we don't take the average. We take generally the mode, or you can take the whatever majority if you want. But there are different ways of doing it. But in this case, if we predicted, say, tree 1 is equal to freshman, tree 2 equals to freshman, tree 3 senior, then junior, then freshman, then we predicted the final outcome will be freshman in this case. Yeah.
Wait, why do we randomly pick columns as well?
What's a good way of putting it? Like I like to think of it as like someone who's trying like we're trying to find follow the leader of some sort. Say each column stands for a different kind of leader, and then one particular column or leader just so happens to be the best generally for most of our data, but it's not the best for like minority populations or subsets of our data. So if we always include that leader inside our decision tree, then we'll overfit or not consider the best way to predict the minority classes.
Have you heard the story of that one competition in like the 1700s where they got everybody to vote for like the best weight on some kind of cow or something like that?
Oh.
Yeah. So it's the same idea here. Basically, like in the minority, like a single person has a really hard time of guessing what the actual weight is. But when you get like a huge number of people, so in a similar kind of context, this like huge number of decision trees, they can actually guess the right example, the right the more accurate value there, just by some kind of analysis that goes on within the forest themselves. So I don't remember the exact name of that. I can try to find that for the next lecture, or actually I'll look it up right now. I'll let you know.
Yeah. And yeah, there's actually like if you think of reality or let's say a political system right now, this lends itself pretty well, and you want to build decision trees that can generalize to all types of data, not just the majority data. So that's why we try to randomize the columns, just as the same reason why we randomize the rows too. Yeah. So the order doesn't matter because so say you have 10 columns, just put in like randomly. Then you pick like 3 of those columns to put inside your decision tree. The way that our process works over here is that no matter which order those columns go in, we'll always find out the column that will produce the minimal SSE or the minimal Genie index. So it doesn't really matter what order they come in. Did that answer your question? Okay, cool. Awesome. So there's that, and yeah, and then the final thing I want to say is that this is the exact same concept of what we refer to as ensembling. So random forest is basically an ensemble of decision trees, and what that means is that basically if you imagine that each decision tree is its own model, then what we're actually doing is basically combining every single model together and considering the prediction of each one. We take the average or we take the mode and majority depending on the class, and then that's our final prediction. We don't need to just do this for decision trees. We can also do this for linear regression. We can do this for logistic regression, KNN, K-means, etc. Whatever prediction they have made, we can combine those predictions with other models, even random forests themselves, to give a better prediction accuracy overall. And this has been done many times on Kaggle. Basically, the winning solution is an ensemble of some sort. So it will include random forest, it will include KNN, a bunch of these models, and then people just combine the predictions, choose the best way to combine them, like take the average, take a weighted average or something like that, and that almost always guarantees you a higher accuracy in the very end. So that's like more advanced level, but I'm introducing it now because the concept is literally built inside random forests and how random forests are made. Okay, cool. Any questions?
The article.
Oh, sure.
Or just something that talks about it. So in like the 1800s, this guy Francis Galton, he went to a county fair. He had this ox with him, and he was like, "I don't really believe that democracy means anything. I believe like me as a smart person can figure out the size, like the weight of this cow better than like a whole group of people. But you know, I might as well test it out." He was still a statistician. He was still scientific. Basically, he gets like a vote of people at this county fair and ask them like, "How big is this? How much does this ox weigh?" And he collected all of their votes, took the average, and then their votes were really incredibly close to the actual value. And so it's that same kind of like phenomenon that happens to occur in the decision forest as well. So yeah, if you want to read more about it, the guy's name is Francis Galton, and he's weighing his ox. NPR did a similar study, and they got very similar results. Apparently, like they put up a picture of a cow on their website, and they asked everybody how much it weighed. And the actual weight was like 1304. The average guess was like 1,287. So it was like off by 20 pounds or something like that, which is crazy. And it turns out the average weight of a cow is like 1,500 as well. So it's not like they could just look it up.
Yeah. So this is again for like just to have an overarching concept. This is what teamwork is for. So multiple minds working together. That's how it works. Cool. Wait, can you launch the Jupyter Notebook for?
I think it's up actually.
Oh, it's already up.
Yeah, check Chrome. Oh, maybe it's bugging out. Nah.
Okay, cool. Awesome. Let's see. Okay, cool. So the final part is to give you a demonstration of how random forest works in code and to compare it with logistic regression. So we're going to be using the Titanic training set that we had before. Again, we're going to import our libraries, data pandas, sklearn, statmodels.api, except we have this line over here, which imports the Python implementation for our random forest classifier. So let's see. Just run these lines. Okay, I'm going to read the data in. This should be the exact same code as you had before during the logistic regression lecture, but much more simplified. We're just going to drop these columns, we're going to just get these dummies, sex, p-class, and embarked. We're going to drop these columns, passenger ID, name, ticket, age, and cabin, so that we can have a very simple data set afterwards. And then we split again according to our local train and local test. And then do our basically the same operation as we had before. And then we run our logistic regression model. Why is this taking so long? All right, well, no, this should be a very small data set. Anyway, so this is supposed to be the output of the logistic regression model. We previously had an accuracy of 80%. And that's basically taking the predictions, which are going to be the probabilities of something between 0 and 1. And we classify something as 1 as being as something that has a probability that's greater than 0.5. And then we equate that to a local test response variable, take the mean of that, and then this is generally our accuracy.
Do you want to try stop interrupting the kernel?
Yeah, let me do that. Wait. Okay.
Yeah, sometimes that happens. Try running it again. We'll use it, I guess.
Okay, yeah. That's weird. Okay, cool. So yeah, okay. So this next line is the random forest model. And notice that it's fairly simple. We have basically the exact same code as we had before, or very similar code, except for like this result equals to line over here. Generally, this is the format that you want for every single other classifier that you're going to build, whether it's KNN or I don't know, SVM or LDA, QDA, etc. This is always going to be the format where we have CLF equals to some random forest classifier or some kind of classifier, do CLF.fit of the train and the local train X and local train Y, and then we do a prediction. Predict underscore proba will give you the probabilities from that classifier, and predict will just give you the actual classes, 1 or 0 in this case, from our test set. So for our random forest, n estimators corresponds to the number of trees or decision trees we have. Typically, you want to have about 400 or 500 trees. That's usually, like, in general, the best number. You can always have more. It doesn't really hurt, but actually it will hurt because computationally it will be very slow. But hundreds is a good number if you want to do things fast. So I'm just going to print out. So this is the output of what preds looks like. Notice that it's contained in an array. The first column corresponds to the probability of the 0th class, and then the second column corresponds to the probability of the first class. And if we had multiple classes, a natural question is, well, how do we figure out like which columns are which for each class? The classifier object itself has a convenient .classes underscore method, and this would generate for you also in an array of what classes correspond to each column over here. So if you did this model again on the Facebook project, for example, you have multiple rows, like a lot of columns, sorry, and then you need to rely on .classes underscore to properly identify which class belongs to which. So anyways, so once we know that this column corresponds to 0 and this column corresponds to 1, then we can subset the, well, I'm just going to pick this column because this is the probability that we get a class of 1, or if someone survived. We subset that column, set that to be greater than 0.5. Anything greater than that will be considered as true or 1. Equate that to local test y, and then we get a final accuracy of 0.826815, which is in the Kaggle world a very big improvement. So if you test this again, like if you run this line again, you get a different set of predictions. You get a different accuracy. If you run it again, you get a different accuracy, and if you run again, you get a slightly different accuracy. And this is because, again, each decision tree is built on a random subset of the data, both row-wise and column-wise. And so that is something that will always be different every time random forest is run. So which is why you always have a different accuracy at the very end. Whereas logistic regression, there's nothing random about it, so you always get this accuracy score for that. And then if you want to like control for the variation, there will be a parameter in random forest called I think set seed or something like that. I forget. Is there a set seed? Or it might be random state or something like that. Basically, you set some kind of value.
Wait, no, I think random state is like the numpy random.
Oh, okay. Then, wait, where's the?
Just Google it.
Yeah, it's generally not that important. But if you want to control for the accuracy value, then there's a seed parameter that you can set. Yeah.
But so if you increase the n estimators, would that kind of the difference between the accuracy kind of go down then?
The difference in what?
Like if you increase the n estimators, like say 400,
Mm-hmm.
Every time you run it, would the accuracy kind of not change as much?
In theory, that should be the case. It will basically reduce the variation, in theory, of our test accuracy. So if we run this, it will take. Well, in this case, it would take. It still doesn't take that long, but if we run that, I get 0.826. 0.82. There's still some variation. I don't know. I'm just saying. You can play around with these parameters however you like, but yeah, it will be around 83% for your test accuracy. And then what you hope is that this will generalize to the actual Kaggle test set when you submit onto the Kaggle leaderboard. Cool. So that's how random forest works. Next Monday, we're going to be talking about the interpretation of random forest, and we'll be using the Genie index as basically the value that determines which variables are the most important. Cool. All right. How are we doing on time? What time is it?
It's 7:35.
Oh, okay. Yeah. So yeah, I didn't really intend this lecture, today's class to go too long. So that's about it. Any other questions? Just come up forward, and Philip and I can answer. Thanks.
That's the like 20 minutes where I dipped out.
Wait, what?
The 20 minutes where I dipped out.
Oh yeah, you went somewhere?
No, I went to go print off papers. Either one.
Oh, okay. Yeah, that's fine. Yeah, that's fine. It's totally fine.
Oh, did we end the yeah. No. I don't know how to stop this. What?
Huh? No, we're good.
Oh yeah, it's usually automatically stopped. Okay.
Stop screen.